Welcome to this video on Cartesian vectors in 2D. So you can certainly extend this into 3 dimensions, and at some point I'm sure that I will in a future video. But in this video, I just want to introduce students to kind of Cartesian vectors. And I have done this already, but I did it indirectly. So where I was breaking down geometric vectors into their x and y components. And that's really what a Cartesian vector is all about. Now, there are certain notations to be able to capture the Cartesian vectors into their x and y coordinates, so you don't have to necessarily separate them. You can almost treat them like you would as ordered pair, so a point, for example, okay, in the x and y coordinates, except instead of a point where we use kind of round brackets, we use square brackets. And you see that in the second point that I have on the screen in terms of the agenda for this video. So I'm going to compare the geometric to Cartesian kind of vector representations. I'll do it with a simple example, and then I'll introduce you to the notations. Okay, so just so that you know, I'll introduce you to the I and j vectors, which really, okay, are just the unit vectors in the x and y directions. You'll see that the addition and subtraction, okay, of vectors in Cartesian planes can be done basically the same way as you do with any points that you would have, okay, and I'll talk about that and what I mean by that. Now, multiplying by a scalar, again, is also something which is really nicely captured by Cartesian vectors as well. The unit vector, which is the collinear to the actual any vector that we have, okay, so that is just division by the magnitude. So you do have kind of unit vectors, and I'll talk about that, and then I'll recall, okay, for you the distance between 2 points. Although you have pretty much done that in grade 9 or in grade 10, but you can relate it back to vectors because of the fact that if you do have kind of 2 points, right, and you're now thinking about them in terms of vectors that you have, then you can find the distance between them, okay, or you can find the magnitude of the resultant vector. So that's what I'm going to try to capture, and hopefully the video won't be super long, but I can't promise you, okay, like many of the other videos that I make. So let's dive in. So the first thing is kind of geometric versus Cartesian representations. So here I present to you a very simple example. So we have a vector, so it looks like it's a force, and this would be the geometric representation of this. Now it's geometric because of the fact that I am representing it in terms of bearings. So the direction is represented in terms of bearings. So if you recall, you have either true bearings, you have quadrant bearings, right? Or you have bearings with respect to the horizontal, which you can go around in the counterclockwise. So within here, so for example, if I would write this out, I would say this is just 5 newtons, and I would say that this is at, and notice that it's set 37 degrees, so I can put it at 0.37 degrees, and this would be with respect to the true bearing, which is the north bearing. Now, I put y and x here. If you were doing this as a geometric vector, you're not really thinking of y and x, although I have used that quite often, but you would think of it as north, east, west, and so on. So this is a geometric representation. Now, if you're going to be thinking about the Cartesian representation, what happens is, and you've seen me doing this, you would break this down into its x and y components. So if I take this and break it down into its x and y components, then what I would find is, right, so that the x component, so this would have been the x component right here, and this would have been equal to, okay, at least in magnitude, to 3, right? So I can think of this as 3 newtons going east, okay, or 3 newtons at 0 degrees. Now my y component, okay, so that would have been, okay, along the y component over here, and it would have been equal to 4. So this would have been equal to 4 newtons, assuming that I am working kind of with forces. It could be position, it could be anything, okay, velocities, doesn't really matter. So my vector in general, okay, so if I would have that, and that should not surprise us. So if I had this as a vector, right, and I'm going to just put it randomly, let's say somewhere over here, then my x and y breakdowns would be just simply, so this is my x, let me just do it as a vector, so with the arrow, well, that's not going to work, okay, that's not letting me, okay, there we go, and then my y, okay, would have been right here, and then you know that these two, if they sum up, the resultant would have been that 5 newtons, okay, at that particular angle. Now, how we represent this, and we would be representing this in the Cartesian plane, so instead of writing it like I did over here, which is the geometric representation, if you wanted to represent this in a Cartesian plane, then we would write it out. So if you were thinking about this being a point right here, so that point, if I would write it out in the Cartesian kind of axes, this would have been nothing else but simply 3, 4. I'm going to drop the unit for the moment. You can add the unit to whatever it is that you like. And that's just an ordered pair, right? An ordered pair meaning that this is just a point. Well, it turns out that if we want to be able to write, okay, so this would have been 3 and 4 over here, and we want to write it as a vector, and we want to let someone know that it is a vector, instead of using these round brackets, okay, as I have right here, then we typically instead will use square brackets. So we're going to put this, and we're going to say this is 3, okay, this is 4. We can put the units in there as well. And this, with the square brackets, will represent an actual vector, if you are talking, of course, about vectors. So these two are equivalent. So both of these representations that you have, so this is the geometric representation, this is the Cartesian representation. And we don't need to put any side in terms of a direction. The direction is already implied because of the fact that you've put these actual square brackets within here, and what you're referring to is, instead of the actual point, you are now actually referring to the vector itself. So that is this vector, which is 3, okay, and then 4 up, and these are the actual components of the x and y components. So that is the distinction, and you can do that with any vector that you like. Right, so you can put them with respect to a Cartesian axis, you can break down into its x and y components, okay, we kind of think of them in terms of their, okay, that they're centered around origin, and then we can go ahead and then work with those vectors directly, right, so that's something that we want to be able to do. Now, here, so if I go back into our agenda, so that's geometric and Cartesian kind of vector representation, and it seems rather simple, right? So here, okay, what we do is, in general, instead of dealing with an actual point, as we would do in this case, as an ordered pair, as soon as we write it in this form, then we are referring to a Cartesian vector representation with these square brackets. Now, the next item here, so this is the I and j vectors. And so what we have, so if you're thinking about this, okay, and in particular, so if you're thinking about that, so these vectors, these I and j vectors, so if you had your Cartesian planes, or your x and y axes, okay, so in this, I'm going to just draw it out in here, the vectors that we are referring to, okay, so this is my vector, okay, and that vector is a tiny vector, and that's actually, so if I write this out, so this is 1. So you will notice that this vector, okay, if I would write it out, this is 1, and it has no y direction. This particular vector is always at a 0 degree to the horizontal, and my x value is 1, and it is a unit vector, meaning that it has a magnitude of 1, and that is referred to as, so we very often refer to this as simply the I vector, okay, so you might see it like this, or you might sometimes see it with a little hat, okay, like that, so it just depends, okay, on who is writing it, and that is just known as the I vector. Now my j vector, so this particular j vector is this right here, so that is now 1, but it is in the direction, okay, of the y, so that means that my x is 0 and my y is 1. And this is referred to as the j vector, right? So you write it like this, or you'll write it with your actual vector representation in that form. And anybody who sees these, okay, because it's just been standardized, the same thing as saying the x and the y axes, and everyone knows x is in the horizontal, y is in the actual vertical. Well, when you say the I vector or the j vector, you know that the I vector is referring to the x, okay, and then the j vector is referring to the y, right? So that is what those I and j vectors are. And now, if you're breaking all of these things down, so within here, then you can say, so for instance, if you wanted to capture this right here, if you wanted to be able to capture this, you can certainly do it with the I and j vectors. And the way that we would break this down, so within here, so you can say that this is really 3, okay, and this is going to go back into the scalar multiplications, for instance, right? So this shouldn't surprise you, right? So I have this, and then I say plus, and this is going to be 4 multiplied by the 1 over here. It's a funny 1, okay, right there. So that's 1. So the addition of this, so being multiplied by a 3, right? So this is simply nothing else but it's saying 3i plus, and this is now 4j. Okay, because those particular Cartesian representations are just your I and j vectors. And this, okay, if you write it in, this is the same thing as saying this, or, okay, it is the same thing as saying that. So you can write it in terms of its I and j components. And of course, if you add them up, so if you're thinking about it, well, this is really 3i, and this is 4j. And of course, it's going to give you the resultant vector of 5, okay, at the direction, okay, that we wrote out there. So that's what we would have over here. Those are the I and j vectors, okay, right there. Now, I have just done, okay, and I just showed you that you can do the addition and subtraction directly with vectors. So what's really interesting is that when we had geometric, right, so if we have these geometric particular representations, it's actually really difficult for us to be able to add them, right? So, if I would have 2 of them, so let's say if I did have, 5 newtons at, and say this is 0.37, and then I wanted to be able to add it to another vector, so let's say maybe this is 10 newtons, but this was at some other direction, and I don't know, maybe this is, let's put it at 0, okay, let's say 95. So if I'm going to be adding these 2 vectors together, it's really hard to do that. So it is actually much nicer to be able to break these things down in terms of its components. And then that's exactly what I was doing, right, in many of the examples, So if I took a harder example, I love to break it down, especially if I had more than 2 vectors, okay, to break it down into its x and y components and then start adding and subtracting those actual components. And I did examples. I can put up a link up above there, even with these particular forces. Okay, so you can see a pretty complicated example there. So now I'm going to just take this. Okay, so let me take this. I'm going to copy it down and bring it in here. And I just want to talk about the addition and subtraction when it is in Cartesian form. Then it becomes really simple, right? So as you're breaking it down. So let me change these. So I'm going to just change these back into its Cartesian representation. So we already know this is 3 and 4, okay? But I don't know this one because I just made it up. So I'm going to do that in fast forward fashion here. So just a moment. All right, so here it is. So, I mean, in terms of breaking it down, what I had to do is, because it's 95 degrees, so notice it's going to be 5 degrees actually, because it's 90 down and then it's 5 degrees. So I just broke it down and then I had to use, cos and sines to be able to find the x and y components. So I've already done that in previous videos, and I'll assume that you are comfortable, okay, with doing that and breaking it down. And now, so this one, for example, so this was just simply 10 newtons and then cos of 5 degrees. And then my y component is going to be negative because it's down. So it's going to be negative 10 newtons of sine of 5 degrees. And then I will know exactly what those components are, and these are right here. Now, if it's in Cartesian representation, I'm going to just remove this, then the addition and subtraction of this is actually really simple, because when you're breaking it down, you would do almost exactly the same thing in terms of adding and subtracting your actual components. So, you know, your x and your x is going to come out together. So this is really going to be 3 and then plus, and this is going to be 9.96, okay, comma. And then the second one is going to be 4 plus, and I guess it's negative 0.87. And that is your y component. So with that, and that means this is going to be 1296, and then comma, and then this is going to be, I guess, you know, so I rounded those, but it's going to be 3 point, and I guess 13, okay, as you're subtracting that one away. And that is your new vector. So this is exactly what the vector would be in terms of the resultant vector of the addition. So what's really nice, what you will find is that the addition that you are carrying out, so if you have a vector, okay, so let's say, you know, we have a vector and this is just the A and the B. So no matter what those are, so the addition, and let's call this C and D, then the addition in Cartesian representation is so much easier. This is just simply A plus C, okay, comma, and this is going to be B plus D. That's all that you're going to be doing. And you can certainly, you know, prove this. You can go back into the additions. You can break this down into its kind of, you know, unit vectors, so the I and the J vectors that you are carrying out, and you'll find out these. Now, for subtraction, so if this is, you know, subtraction right here, okay, so if I put a subtraction in there, then that doesn't change anything for me, actually. So if you know, or if you recall, so subtraction, of course, is kind of represented as, in terms of vectors, so if this is AB, it can be represented as a plus, and it's going to be the opposite, right? So it is the opposite vector. Well, the opposite vector is going to be just negative C, negative D. That is the opposite vector within here. And so if you do this, you know, you can certainly do the addition, and now you're stuck, and you're going to be doing A plus, you know, negative C. That would have been your result, and then B plus, and then negative D. And there you have it. So additions and subtractions in Cartesian representations are beautiful. Once you have them in terms of their x and y components, you know, you can find out what the resultant vectors are. And that's really, really nice to be able to see that. All right. And then if you wanted to change them back into geometric, you can, right? You can find your angles, you know, you can find your magnitude, okay, of that, and so on. So that is something with regards to thinking about this addition and subtraction. Now, what about multiplying by a scalar, right? So what if you're multiplying by a scalar? Now, if you recall, so if you take any vector, so within here, so what we had, so if you have a vector, let's say the vector is V, and then you come along and you start multiplying it by some scalar K, well, what we had found is that, you know, this particular vector V, so let's say that is V right there, and then you multiply it by K, all that happens, right? So all that happens, I'm going to duplicate this. You get the same vector, but now it's scaled, right, in magnitude. The direction doesn't change, except, okay, by that K, right? So whatever, if K is bigger, okay, than 1, okay, or if K is smaller than 1, now if K is negative, then it will change its direction, and it's going to head in that direction. But that's all that scalar multiplication did. Now, if you are talking about the actual representations where maybe V, so now let's say that, you know, V, and I'm going to break this down into its x component, okay, and then into its y component. And now I have the Cartesian representation. And now you come along and you're going to be multiplying by k. Well, guess what happens? It's basically like distribution. So you're going to be distributing across. And really what you have now is you have just k, v, k, x. And then this is going to be k, v, y. So the x and the y components just simply get scaled by k. And that's exactly the same thing as before. But it's just so much nicer to be able just to simply say, okay, well, now we have our k, and now we're going to be scaling this along, right? So we just distribute it into our vector. And then if k is negative, well, that's going to impact the actual v and the y components because it's going to be multiplying by a negative. So that's scalar multiplication. So that is beautiful, right? So for instance, if I had my original vector there, 3 and 4, okay, and then I wanted to be able to scale this, let's say by 2, well, all you do is you bring this inside, and what you're going to find is, okay, so this is going to be 6, and then this is going to be just simply 8. You've now scaled it by 2. Now, look what happens in here. So if you wanted to find its magnitude, which, so if the magnitude of this, okay, for instance, if you wanted to find that magnitude, so the magnitude of this particular vector, well, so that would have been, 6 squared, okay, so that is the x component, plus, okay, its y component, which is going to be 8 squared, and then, so the magnitude itself, now you're going to take the square root of this. Now, why? Because, okay, so if you're thinking about it, these are just the x and y components, and really what you're doing is you're using the Pythagorean theorem to find the hypotenuse, so the actual length that you are carrying out. And within there, so if you do this multiplication, so notice, so let's just kind of do it for purposes of showing you what is going to be happening. There's going to be square root of 6 squared, which is 36, plus 8 squared, which is 64. Okay, and now of course this is going to be equal to just simply square root of 100, which is 10, right? Now, what was the original? Well, the original, so the magnitude of this was 5. Now we knew that, right? So if I go back in here, that's exactly what it was. It was 5, so it was just scaling it by 2. So that's exactly what happens here if you're scaling it by any vector, by any scalar. So just you bring it inside, and that's all, okay? That's all that you actually have, which is pretty neat to be able to see that. Now, there is something that you should be aware of because, we do want to find collinear vectors, and in particular, the unit vector that is collinear to any vector. So what we are referring to is this. So if you take the original, so if you took, so here it is, okay, so let's assume that this was the 5 newtons, right? So it had the x component, and this was 3, and then this was the y component, which is 4. So if that's the vector, and let's call this vector v, okay? So this vector v is, so 3, 4, or you can write it in geometric form if you wanted to. So if you want to find the unit vector, the unit vector, which is collinear to this, it means it's a vector which has exactly the same direction, but its magnitude is 1. So that's unit. The word unit will mean 1. So it means it will be a vector which is in the same direction, okay, but it is equal to 1 in magnitude. So, so this would have been 1. So if this was 5 newtons, this would have been 1 newton. But it's collinear. It's in the same direction. Now, of course, you can find a collinear vector which is in exactly the same direction, or it's 180 degrees, okay, meaning that, you can have this. This is also a collinear vector, except, okay, so within here, let's see if I can, draw it. Okay, hopefully it's approximately in the same direction. Doesn't look like it. Okay, let's take a look and see if I make it collinear. There we go. So both of these are collinear. They're in the same exact, okay, kind of plane, okay, or line, so they're in the same line, so collinear, so the same line, and they're either in the same direction or in the opposite direction. So there's always two unit vectors, okay, with magnitude of 1 that are going to be collinear. Now, how do you find, okay, and find out what this is? Now, of course, we already knew that this was 5 at 37 degrees, at least to the true, with the true bearing. But if you wanted to be able to find it from right here, then all you have to do is you take the vector, okay, itself, and you divide it by its magnitude. So you would take the vector, so this would have been 3, okay, over 4, and you divide this by its magnitude. And that will make it a unit vector. And that should make sense to you, right? Because think about, if you're dividing by the actual magnitude, and now you wanted to check if it's a unit vector, meaning the magnitude was 1, so that means you had to find the magnitude of this entire thing. Well, if you find the magnitude of the entire thing, okay, and you're dividing by the original magnitude of 3, 4, so you're going to have, okay, the magnitude of v really divided by the magnitude of v, which is going to be equal to, okay, so 1 divided by the same thing is just equal to 1. So let's try this out, so I mean 3 and 4, so the magnitude, we know the total magnitude is 5, so that's easy to see. But if you wanted to remember, so for any vector, okay, this is always equal to the x component, okay, squared, plus the y component squared, and of course, okay, the square root, just by Pythagorean theorem, okay, and then knowing what that distance is. So that is the magnitude overall. Now, we already know this is 5, right, in magnitude. So this would have been equal to 5. So the unit vector, okay, is going to be either, so 3 over 4 divided by 5, and it can be this, which is going to be the red one, because it's in the same direction, or it can be negative. So you can certainly put it as negative, which would mean that it is the blue one. So these are collinear, because they're in the same line, collinear. They're in the same line as the vector, but they are called unit vectors, so unit vector, because of the fact that its magnitude is equal to 1. Right? So the magnitude of this is equal to 1. So within here, and you can see that. So this is going to be, if this is equal to 5 in the denominator, so really this is just simply 3 over 5, okay, all over 4 over 5, right? So that's the vector. And now if you take its magnitude, so if you take 3 over 5, square it, plus, okay, 4 over 5, and you square it. So if you do this, you will find that this is just equal to 1. And that is called a unit vector. So the word unit vector just means that it has a magnitude of 1. Okay, a collinear unit vector means that it's in the same direction as your v. Now, the easiest unit vectors to work with are, of course, I and j, right? Because I, we know, is equal to 1, 0, so it's very easy to see that it's a unit vector. We don't need to do any calculations, okay, just because this being 1. And then our j, right there, which was equal to 0, 1, is also a unit vector. Those are the simplest unit vectors. Those are kind of, sometimes we call them as base vectors because they define our Cartesian plane. So that's what we have in there. Now, another concept, okay, that kind of we will finish off this video with in terms of this introduction to these Cartesian vectors is I just wanted to draw your attention when you are calculating, for example, what the distance between, well, 2 points, or what the magnitude between two vectors is. So if you recall, if you take two vectors, let's say if I would draw them out and you're thinking of them as drawing them out. So let's say this is one vector, okay, and then let's say maybe this is the other vector. right? So if this was here, and then so I'll call this vector v1, and then I'll call this vector v2. Now, if you wanted to know, what the actual resultant is, you can certainly add up these two vectors and then find out. But, okay, don't forget that if I wanted to do this, which is, let's say v1 minus v2, so if I wanted to do that, okay, within here, then this actually would have been, okay, so as you're going through this, okay, that's the resultant vector, okay, and that resultant vector would have been this vector right there, right? And remember that, subtracting v2 really means that, we're going to be doing the opposite, okay, to this vector. So if I took this vector, let me just take it right here, and then I'll do the parallelogram. So if I take this, I duplicate it, but, okay, notice that if I take its negative, right, so it's negative, so that means this is going to be going in this direction, okay, so that's going to be right there, right, so that's v1 plus the opposite of v2, okay, so that's what I have right there, and therefore, so my result, okay, would have been this right here. Okay, so this is my actual result, okay, that I have in there. So from here, let me just take this one, okay, and then put the result, because I went from v1, so I'm going to just rotate this around, okay, bam, okay, and then that's my resultant. Now, if you wanted to find what the magnitude of this is, right, so what that magnitude of this is, well, you would have, so this would have, so if in Cartesian form, so this right here and this right here, so this would have been points, right? So along here. So for example, v1, okay, so this would have been, so I'm going to write v1, its x component, and v1, its y component, right? Now if I write it as a vector, I'm going to square the brackets in here. If I write it as a point, so if I was writing it as a point, let me erase this, there's no confusion. So if I'm writing it as a point, okay, then I would have simply written it out as, okay, so this would have been those values, okay, that I have, and let's, so we'll call this, the v1x, okay, and v2x. And if I write this as a point and break it down, okay, so that's v2 x component and v2 its y component. Well, the magnitude really is nothing else but the distance between 2 points. So if this was point 1 and this was point 2, we know what the distance between 2 points is, right? We have done that, and I can put up a link up above there, okay, to distances between 2 points, okay, in terms of the video. This is going to date you back to grade 9 or 10. But for vectors, we can do the same thing, right? So the distance between 2 vectors, okay, that you have, you can always find it. And that is just simply finding the magnitude, okay, between, so notice here I put P1, okay, and P2. So what is the vector between those 2 points? And the magnitude is nothing else but the subtraction. So if you would be doing this, okay, this should kind of be a deja vu for you. So I'm going to go back in here. So within there, so if you have those 2 points, okay, so let's call this, I'll call this point 1. I'll just refer to x1. It's going to be y1, so that's point 1. And then point number 2, okay, let's say if I put it as x2 and y2, of course the distance between them, so if you are going to be taking the distance between these 2 points, it is simply the square root, right, of, and then you can just go x2 minus x1 squared plus y2 minus y1 squared. So this is a complete deja vu in terms of that. But if these were vectors, you would do the same thing, right? So you would just simply subtract, okay, to know what the actual differences are, and then you would find out what the result is. because what you would have is the vector is actually x2 minus x1, comma, y2 minus y1. Okay, and that is the vector. Well, and if you want to know what the magnitude of that vector is, this is exactly what you would do. So I want to just leave it with that. I'm not going to, give an example. I believe that, distances between 2 points is something that you most likely should remember. And if you don't, you can go back to that link, okay, to take a look at some examples within there. All right, so that is the kind of introduction to these Cartesian vectors. And it's certainly, the highlight is that we represent them in this form, so they almost literally look like, okay, a point representation or an ordered pair, but we just put the square bracket to make it now very obvious for the reader that you are referring to vectors. And then we treat those vectors in additions, okay, subtractions, kind of the same way by just working with the components directly. And then we can multiply these vectors by distributing into the x and the y components. All right, so thanks for watching, and we'll see you in a future video. Bye, everybody.